All right, everyone, let's go ahead and get started. So our next research presentation comes from Purdue University, University of Michigan, and the University of Minnesota. So the first speaker I want to introduce is Professor Yiheng Feng, who received his Ph.D. from the Department of Systems and Industrial Engineering at the University of Arizona in 2015. His research areas includes connected and automated vehicles and smart transportation infrastructure with a focus on intelligent traffic control, transportation system cybersecurity. He has served as a PI and co-PI in many research projects funded by NSF, USDOT, and USDOE. He has published more than 50 research articles which appeared in top journals including Nature Communications, Transportation Research Part B and C, and IEEE Transactions on ITS. He is the co-chair of the Traffic Signal Systems Committee Simulation Subcommittee at the Transportation Research Board and serves as an editorial board member of Transportation Research Part C. He's the recipient of the inaugural Best Dissertation Award from the Chinese Overseas Transportation Association in 2015 and Informs ITS Best Paper in 2021. Our second presenter is Dr. Morley Mao. Dr. Mao received their BS, MS, and Ph.D. degrees from the University of California at Berkeley. They are a recipient of the NSF CAREER Award, Sloan Fellowship, and the IBM Faculty Partnership Award. They have been named the Morris Wellman Faculty Development Professor. Their research interests encompass network systems, mobile and distributed systems, and network system security. Their work involves both empirical data collection and analysis, as well as the design and implementation of new systems. And our final presenter is Professor Zhili Zhang, who is a Distinguished McKnight University Professor and Quest Chair Professor of Computer Science and Engineering at the University of Minnesota and the Associate Director for Research at the Digital Technology Center. Dr. Zhang received a Ph.D. degree in computer science from the University of Massachusetts. He joined the faculty of the Department of Computer Science and Engineering at the University of Minnesota in 1997, where he's currently the McKnight Distinguished University Professor and Quest Chair Professor in Telecommunications. He currently serves as the Associate Director of Research. That's duplicative. Sorry about that. Professor Zhang's research interests lie broadly in computer and communications networks, internet technology, multimedia systems, and content distribution networks, cyber-physical systems, and Internet of Things, and applied machine learning and data mining. Professor Zhang has published more than 100 journal and conference workshop papers, many in top venues in networking and related fields. Without any further ado, please welcome Professor Zhang, Professor Feng, and Professor Mao. Thank you.
I didn't know you're actually going to read our bios. So I'm going to kind of start first. And so this is going to be a joint presentation with my colleague, Molly and Yiheng. So we try to kind of share you some of the thoughts and some of the prior work, mostly done by Yiheng and Molly on some of the cybersecurity issue for CCAT. So this is basically a kind of agenda to outline our talks, right? So I'm going to start first, give you some kind of background on the connected and automated transportation system, and give you an overview of some of the cybersecurity challenges, especially some of the newer kind of cybersecurity challenges. Then Marty going to take over, talk about some of the attacks and the defense for vehicle system, in particular cooperative perception. And Yiheng going to actually talk about attacks and defense for the transportation infrastructure system. I would come back and try to kind of put everything together, share you with some of the thoughts we have, and say how we can actually secure and harden the future CCAT ecosystem. Right? So again, so I'm going to kind of quickly go through the background. Right? So we all know that driverless cars are here, otherwise you won't be here. And we know the autonomous vehicles, and including kind of not only just the cars, but also buses and others have been testing. And we already have robot taxi services, right, provided by several vendors. And also we have Tesla self-driving. Right? So personally, I think probably from the vehicle point of view, individual passengers, self-driving probably going to be something that's going to come to individual drivers first, right? So what is really exciting is not just the autonomous vehicle, right? So what is really important is with the advanced communications, cloud computing, edge computing, and also AI is the ability to building next generation connected automated transportation systems, right? So not only make the cars much smarter, but also make our infrastructure much smarter, and also make the travelers, the road user much smarter, right? So this is all enabled by advanced communication, edge and cloud computing, and AIs, right? So obviously this, with such a kind of smart, connected automated transportation system, we actually can enable a lot of new services, right? For example, we can achieve zero fatalities through, for example, cooperative vulnerable user protection, right? And also enhance the traffic efficiency and make mobility equitable and accessible. So also minimize the impact of transportation on the environment, and perhaps many, many new type of services we yet to imagine. Right? So this is basically the vision we're actually working for. Right? These visions are good, but we know there's still a huge gap from what we imagined and from today's what we have. Right? So we know that autonomous vehicles still a long way to go to reach full autonomy. And also in terms of intelligent road infrastructure, we don't really have a lot of CV2X and other kind of things deployed. And in terms of communication, right, so the communication actually, if you just based on the CV2X, has a very limited capacity, only 30 megahertz capacity, not going to be sufficient to enable a lot of kind of interesting application we are thinking about. Right? And in terms of edge computing, it's largely not being deployed yet. Right? So more importantly to the theme of this particular talk is how do we actually secure and harden the CCAT ecosystem. Right? So we know that the transportation system is actually a complex, diverse system of system. Right? Just looking at the vehicle themselves or the road user, right? So the vehicle itself is actually a very complex system itself. Right? And you also have many different type of road users, right? So how do you actually harden and secure such systems is challenging, right? So other things, you also have a diverse and dynamic physical environments, road infrastructures, etc. Right? And V2X and communication technology also constantly evolving. And also edge, how do we actually leverage edge and cloud computing platforms itself is actually a lot of challenges, right? So basically, we really need a holistic kind of systematic framework to think about how to secure and harden such a system, right? So let me just kind of change the gear, talk briefly looking at what are the cybersecurity, generally the security challenges, right? So not just cybersecurity, but also physical security challenges, right? So I'm going to just provide you a broad view, right? So if you look at from the CCAT system point of view, you have several kind of constituent system, right? So you have vehicles and other road users, and you also have physical infrastructure, road and environment. And you also have to rely on communication infrastructure to provide connectivity and also cloud computing platform. Right? So we need to secure all the entire system, right? So how can we actually harden and secure individual system, but more importantly, how do we actually prevent, for example, insecurity or vulnerability from one type of system spread to other type of system, right? So if you're looking at from the key building block, how we're actually building such a system, right? So we're going to have hardware and software. Right? So there's a lot of work have already done in looking at how do you actually secure hardware or software system, right? So one thing is, how can we actually leverage a lot of things that have been already developed, software and hardware, to make the system secure, right? More importantly, because we're actually looking at a system that's going to communicate with each other, how do we actually also secure the communication and the data and AI models, right? So what are the kind of new security and countermeasure we actually needed to actually secure such a system? So if you look at just simply from the threat model point of view, right? So you had to think about threat agent, what their motivation, what type of impact the attack going to have, and what kind of capability they have, or how likely probable such an attack going to happen. Right? So for example, you're going to have an individual hacker, criminal can be very different from, for example, organized crime, who may actually want to, for example, take over a certain transportation system as a ransomware. You have to pay for it, right? So motivation may be financial, but on the other hand, if you're a terrorist organization or nation state, they might be quite different, right? So we had to think about those things in order to secure the entire system. So if you look at what type of, with this cooperative system, right, what type of new attack might happen, right? So those can be physical attack, right? So attack can be individual vehicle components, or someone could actually hijack one vehicle themselves, or tamper with environments and manipulate environment to fool your AI systems. And in terms of cyber attacks, right, so again, attack can happen, focus on individual vehicles. For example, the software module for some of the AI algorithm, right, or focus on cloud computing platform, communication, infrastructure, etc. So important part is that because we're thinking about a cooperative transportation type of system, you could also have attacks on the traffic infrastructure, for example, signal control, coordinating the RAM meters, cooperative perception systems, right? So cooperative driving systems, right? So those are all kind of new attacks, and in particular, communication, data, and AI become really important. So I'm going to actually hand over to Molly. She's going to provide some examples and talk about how, with a cooperative kind of perception environment, how do you protect the system?
Thanks, Zili. So I'm going to talk about some more details of some of the research studies we have conducted in my lab in collaboration with our collaborators. So first of all, we're talking about connected and automated vehicles, right? So we're looking at basically within the vehicle, there's a communication system. And between vehicles, there's this ability to communicate between the vehicles themselves as well as between the vehicle and the infrastructure, and potentially even between the vehicle and the pedestrians. For example, pedestrians carrying a smartphone, they could get signals, for example, some alerts when unsafe conditions happen. I want to just remind everyone about this challenge we face, given that machine learning models are increasingly used, right? So we depend on machine learning to perform well, especially from the perspective of perception. So there is this well-known attack, basically this adversarial machine learning attack. Essentially, it's about when you have an image of a panda, if you add some of these perturbation to human eye, the resulting image still looks like panda. However, the algorithm actually misclassifies it as gibbon. In fact, with very high confidence, right? Going from 57.7% confidence to almost 100%, 99.3% confidence. This basically tells us machine learning models are imperfect. We really have to be careful to understand why, how to prevent these models from potentially abused. Right, so now it's very safety critical functions these machine learning models are performing. And for object classification, maybe it's not a big deal. We misclassify panda as gibbon. But however, you can look at an example of, this is a known research study looking at a stop sign image, adding some perturbation, adversarial perturbation. As a result, the algorithm misclassifies as a yield sign. And now we have really a serious challenge. We have to make sure these things do not happen very frequently. We can ideally want to proactively prevent these models from being attacked and potentially compromised. So just a quick overview. Some of you are probably very familiar with this. I want to just go through this autonomous vehicle perception data processing pipeline. So we have on the vehicle system typically multiple modes of sensors. For example, camera sensors, radar sensors, and also oftentimes LiDAR sensors. I know Tesla does not use LiDAR, but actually LiDAR is actually very powerful mode of sensor. So we look at the processing pipeline, right? We have the perception, which allows us to do object detection, position, speed inference. And the object detection is a very critical component. And subsequently, the data output from the perception module gets processed to the prediction, which predicts the object future path, and do the planning, which is looking at the ego vehicle's future path. And finally, outputs the control commands determining how the vehicle should move, right? So and also just bear in mind, this is a real-time system. So we really have to make sure to understand any kind of mitigation against potential attacks. it has to be able to perform in a real-time fashion. For example, looking at LiDAR, LiDAR is typically at the frame rate of about 10 frames per second, right? So ideally, we want to be able to make sure we make decisions at each frame level, because otherwise it'll be too late by the time you make a wrong decision. So keep that in mind whenever we think about both attacks as well as defense. So this is some of the work we have done in my lab in collaboration with my research, my collaborators at other universities. Looking at basically, we have demonstrated it's in fact possible to attack the AV perception software. So this really makes you worry, right? Basically, from our perspective, we want to understand if attack is possible before we understand how do we defend against these attacks, right? So we're thinking about from the perspective as an attacker, and in this case, we looked at Baidu Apollo open source software we were able to get access to, and we were able to demonstrate it is possible to create these attack scenarios where the inference, the object detection result is compromised. So our goal is really to understand the attack and subsequently come up with mitigation solutions. So I want to just quickly go through the related work on perception. So in fact, the camera-based perception work has been, the security of that has been widely studied. In fact, as Professor Zhang just mentioned, there are cases where you can fool the model and be able to infer, basically inject wrong information, causing the inference to be caused to in this case, it will infer a car instead of this, this image on the ground, right? So this has been demonstrated. This is vulnerable, but actually, in fact, there is not a lot of work looking at LiDAR, because oftentimes we say, hey, let's use a camera sensing as well as LiDAR sensing. Use sensor fusion to have better results, more robust output of the perception, right? But the question is LiDAR sensors more robust? It turns out there has been work talking about there are ways to physically attack LiDAR sensors. In this case, what we're showing here is this, basically there is a LiDAR sensor. It does this rotation. How LiDAR works is that essentially it's looking at the reflection, the echoes of the laser beams, right? So when you have a normal object, you have these reflection beams, lasers coming back to the sensor, and as a result of that, the sensor can infer there is an object. So what happens if there's a LiDAR spoofer which artificially injects these lasers into the sensor? And it can it can impose specific delays, and it can change its location. Obviously, this is a physical attack. So it requires an attacker to be physically close to the vehicle where it's actively attacking. So we have demonstrated that it is in fact possible to carry out this attack, even though it looks like it's a very complex attack. But when we started off just translating this idea of this attack into an actual software system on a real data processing pipeline of Apollo Baidu software system, it turns out it's not that easy. So what we found is that there is this key insight. We have to formulate this attack as an optimization problem. So attacker has to be smart enough to use this global spatial transformation function to model the attack capabilities. So just ignore the math. Basically, there is some kind of intelligence going on for the attacker to inject points strategically, causing it to create this fake vehicle. Okay. So in other words, these attacks are not very easy to carry out, but still, if someone is very motivated, it is possible to carry out such attacks, right? So what we have demonstrated is on the actual software system, we have the Baidu Apollo software system. So we have an example where we run the software, and obviously we're not really doing the physical attack of a real vehicle, but we try to do this as realistic as possible. And in this case, we're able to create a impact in terms of causing the vehicle to perceive there is a fake object and causing it to not able to move. Sorry. Let me just quickly do this demo of, let me see. Okay, I think the video is not really correctly embedded. But anyway, basically the video is supposed to show you that the vehicle actually saw an object in front of it that's actually a spoofed object, and as a result that it is stopped at the stop sign. And then there's another video which shows you the vehicle suddenly had to brake, even though there's no real object, but in fact it's a spoofed object. So actually, when we studied this further, we thought, hey, creating an object is maybe not as unsafe as compared to removing the object, right? Because if you remove a pedestrian, remove a real vehicle, then it can cause serious problems where the vehicle could crash into another vehicle. So we also looked at the object removal attack. It turns out that's also possible. And what's interesting here is that we have a software system, right? So the LiDAR sensors is perceiving the object, but it turns out it relies on the software to decide whether the perceived object is really something that needs to be paying attention to. So there are these operational threshold, minimal operation threshold, which is used across the software stack, both in the sensor itself, as well as the middleware, and finally in the autonomous driving framework. And if attacker is smart enough to create these spoofed points and causing the real object to be ignored, then we have a problem here. So let me explain how this works. So I will show you basically the principle behind this object removal attack for LiDAR sensing. So essentially what happens is on the left-hand side, we have a known attack scenario. So there is a actual obstacle. This is its location. So this is the LiDAR kind of 3D point cloud visualization. And this is the actual LiDAR sensor. And the LiDAR sensor is able to detect the object, okay, in this case. And when the spoofer starts to spoof the points, what it tries to do is it creates points very close to the LiDAR sensor. And because what happens with the sensor is that by design, it will prioritize points that are close to it and ignoring points that are farther away, right? Which kind of makes sense because points close to the sensor are more likely to be more critical, of more high importance. It's more likely to be, find a more accurately detectable object. And as a result of that, and you probably would have guessed, and that caused this obstacle points to be ignored. And because of the spoofed points is below the threshold of what's considered important, and those points that are spoofed are also ignored. Okay, so I want you guys to take away from this slide is that we rely on software systems, right? Because the software has these thresholds set, and combined with that information of how the threshold is set, the physical attack can be smart enough to cause those thresholds to be abused in a way. As a result of that, in this case, the object is ignored. This is a so-called object removal attack. So that's all scary, right? Obviously, you can argue, hey, let's combine the camera together with LiDAR and maybe even another sensor modality, radar. And the more sensing you have, the more likely you will be robust to these attacks. That's all true. We can have very robust sensor fusion algorithms. However, these algorithms, sensor fusion algorithms, are also potentially susceptible to various attacks. And when the sensors do not agree, you have a problem, right? You don't always understand what's the right thing to do, whether the object is there or not. So ideally, we want to be able to improve our software system to be more resilient against these types of attacks. So we studied these kind of attacks, and the question is, hey, let's figure out how do we improve the machine learning model data processing pipeline and improve the machine learning models themselves to make sure these models are not easily abused or attacked. So we start looking at the key kind of insight we have is to leverage some kind of property which tells us these physical invariants, right? So in this particular example, what we have is we're trying to take advantage of this property, the so-called free space-based invariant. If you have an object that's spoofed, then you have this inconsistent behavior where the so-called free space essentially is a straight line from the sensor to any of the points in the point cloud. Okay, so the blue area is the part that is essentially is the free space. That means there's no physical object. Okay, so if you have an actual object, because of the intra-occlusion or inter-occlusion of the object within this the valid bounding box, you will have a limited amount of free space, right? Which makes sense. You have a physical object, therefore there's not much free space available. But if you have a spoofed object, as a result of that, you will see a large portion of the free space inside the fake vehicle's bounding box. And here you have an anomaly, right? So basically you have some inconsistent behavior which tells us, hey, this may not be a real object, okay? So we just want to give you this high-level idea why physical invariant is actually a very powerful kind of property we could leverage to improve machine learning robustness, machine learning model robustness. So what we end up doing as an initial step is we added this anomaly detection module called CALO. Essentially allows us to detect these inconsistent behavior in the output of the machine learning perception model from the initial results. And arguably, one could say that, hey, why don't we improve the algorithm by integrating this anomaly detection into the algorithm itself? That's actually our ongoing work, right? Because ideally, we don't really want to have another component, but having another component is also beneficial in that we don't have to retrain the model. It's something more easily deployable, okay? So this is something that we have explored, and results in terms of the actual evaluation results, we're able to see that we're able to detect prevent these attacks from happening with from 80% success rate down to 5.5%. And at the same time, we are not really compromising the accuracy of the machine learning model performance, which is really important because we don't want to add this additional support of being secure, but at the same time compromise the accuracy of the models themselves. So some figures is basically showing you as the attack capability increases, as the number of spoofed points increases, what happens is that the attack success rate also goes up, but it's not really going up that much. It stays below 10% or so. And we also have pretty high precision and recall from this algorithm. So one could argue that it's very hard to carry out attacks where you can spoof a lot of data points, right? Because that requires the sensor to be very close to the physical sensor of the target victim. So therefore, those attacks are much less likely to be carried out in the physical world. Okay, so you may ask, hey, this is for defending against object spoofing attack. And similarly, we can have a similar approach to defend against object removal attack. I won't go into details, but at a high level, it's also taking advantage of some physical invariants, right? In this case, we have these kind of shadows. If you have real objects, then you have corresponding shadows, right? So if you have some shadow that's not associated with any object detected because you removed the object because of the attack, then you know something is unusual. It's likely some anomalous behavior due to the attack. And similarly, we also have a property called azimuth, which I won't go into details due to lack of time, but I do have papers on this topic. If you are interested, I'll be happy to share with you. So let me switch gear a little bit. So we've been talking about this connected nature of these vehicles, right? And vehicles are able to communicate with its environment, with another vehicle, and with the RSUs, right? So with the infrastructure. So that's very powerful. Why don't we take advantage of that, right? So for example, in this two cases, you have occluded pedestrian. So vehicle one is driving, but it cannot see the pedestrian. If it can get some information from vehicle 2, then this would cause this vehicle 1 to slow down, with resulting much safer driving scenario, right? So, and similarly, you have a far away obstacle. In this case, there is a vehicle that's out of the sensing range of vehicle 1, and vehicle 1, not knowing that vehicle 2 is right behind it, it can slow down if it's able to communicate that information from the vehicle, from the red vehicle. So essentially, if we can share information between the vehicles themselves in the nearby location, you can have much safer driving behavior, right? So this is the key idea. But at the same time, we may ask the question: are the vehicles trustworthy? What happens when a vehicle injects falsified information? So we have to be very careful about this, using this cooperative sensing idea, making sure that the data we collect, we receive, has to be verified. You have to make sure the data is actually trustworthy. Otherwise, other vehicles that's untrusted can inject falsified information. So we start looking at this collaborative sensing idea. Essentially, we're looking at, can we do this inference in the single LiDAR cycle, right? Remember what we talked about in the beginning of this presentation? Essentially, the idea is that you have to make sure it's a real-time perception system. So in the single cycle, LiDAR cycle, in this case 50 to 100 milliseconds, can you get the data from other vehicles to help you make safer navigation decision, right? So in this case, we have each vehicle has its own LiDAR sensing capability, and it does this pre-processing using DNN. And as output of that, we can generate a feature map. Essentially, it's a concise representation of its environment. And if you have collaborative perception, you can combine the feature maps from other vehicles through communication when it receives from other vehicles information and do the post-processing. And combine other vehicles' feature maps, you can generate a more complete environment, right? Information about the environment. So this is the key idea, right? So you can argue that there's some variation you can do. For example, instead of sharing feature maps, you can share some raw data, right? Raw sensing data. But sensing data, like LiDAR, is very large, so it requires a lot of bandwidth. So in general, it's not really possible to share those data in real time. So what we did is in the upcoming USDOE Security Conference, we have a paper which essentially looks at, is it possible to attack this collaborative sensing, collaborative perception system, okay? So it turns out it's not as easy because it's a real-time processing system. So if you want to do this optimization from attacker's perspective, you have to get the feature map from the actual target victim information in order to be able to generate the malicious perturbation, right? So there is this kind of very challenging problem that attacker has to have that information in time in order to create this spoofed information. So it turns out attacker cannot do that if you just look at the timeline. So to attack, in this case, to attack the perception results generated right here, this is post-processing, right? After fusion of different vehicles' feature maps, you generate the post-processing decision, right? The malicious feature has to be finished at this time, in order for this to influence the actual fusion results, right? But it turns out the vehicles itself, the feature map cannot be delivered in time to the attacker, right? So there's this delay because communication takes time. So instead, a smart attacker, what it can do is use a previous frame's feature map, okay? So obviously, it's not as accurate as the current frame's feature map. But however, it is possible to carry out such an attack. So again, in this case, we're trying to think like an attacker to show whether this kind of attack is indeed possible. And if we see that it is possible, then we can come up with defense solutions more effectively. So I'm just going to show you this, the main idea of this proposed attack scheduling, which essentially is about taking, so I'm showing you at the top is the frame I-1, and this is frame I. Attacker wants to create this perturbation at frame I, but it can only use information from the previous frame, okay? So it has to do some compensation for the time difference and for the motion that has happened since the last frame. So this is essentially we use motion prediction, and we use optimization results from previous frames optimization outputs for efficiency, because we have to make sure this computation is not heavy weight enough, too heavy weight to prevent the vehicle from doing this kind of local computation, because you cannot rely on the cloud edge computing to do this computation because the overhead would be too high. Also, we are essentially modeling this as an optimization problem again. So again, there's this loss function formulation. Attacker is trying to create this very targeted attack, cause the maximum overlap with a given target with high confidence score. So if you compare the previous result where the attack is untargeted, you have a lot of these red boxes which are spoofed kind of objects, and which is very easy to detect with any simple anomaly detection system. And in the smarter approach, you have a targeted spoofed attack, and this is much harder for defense solutions to be able to mitigate. So I think I'm going to skip this part of the detail. So we also use basically a optimization to leverage previous frames result in order to make the attack real time. So I presented to you something essentially to show, hopefully you're convinced that this kind of attack against the collaborative perception system is indeed possible, right? So then the question is, can we defend against this kind of attack, right? Because we want to take advantage of this communication to share information across vehicles, but we want to be able to trust this information. So can we make sure we receive the information, we still able to detect if there's any malicious injected information. So the idea is very simple. If we have a very small number of vehicles which are malicious, we can leverage some kind of majority voting, right? So we can detect inconsistent behavior. Essentially, if we see an object on the in the free space, this means that there is a potential spoofing attack that happens. So essentially, the vehicles share this information. If there's any inconsistent output, we know that potentially some vehicle is injecting spoofed information on the feature map. Obviously, this is not as perfect because what if the vehicle that injects falsified information is the only vehicle able to see that information, right? Then it becomes very difficult to detect that. So what needs to happen is that the algorithm that merges the data across vehicles needs to have enough redundancy to be able to trust that information, right? If a single vehicle is telling you, hey, that's an object, maybe conservatively you should assume that's an object. But if a single vehicle tells you there's no object there, and there's some inconsistent result from other vehicles, then you should assume that the other vehicle's information is more likely correct. So we were able to leverage the MCD testbed, which is a really great resource for our research work here. And basically, vehicles like this is just an example with LiDAR sensor, with camera sensing information. So we're able to take the traces and collect that information. And we did a 5-car experiment in this case to show that unprotected right turn at an intersection can be blocked from a spoofed vehicle by spoofing the information. So this is running again through a simulation framework, and to show, because we can't really create an attack in the actual vehicle, but we're able to collect the traces and run the sensing data and run the actual algorithm and to show that this attack can happen. Just to sum up this part of the talk, essentially what I hope to convey here is that machine learning models are very powerful, but at the same time, we have to be very careful about making sure these models, the output of models are trustworthy, right? So there are ways to spoof data. For example, for LiDAR sensing attacks, even for collaborative sensing, it is possible to inject falsified information. So the machine learning data processing pipeline, if you look at the end-to-end output of that data processing pipeline, we have to be sure that the whole system is robust. So there's a lot of research in like certified robustness in the machine learning community we can leverage. But at the same time, we have to take a system perspective because it is a networked system that we are working with. So we have to combine these kind of advancements in the machine learning community and make sure they are, I guess, they're used in an effective way in order to create this robust and secure system while taking advantage of the advancements in AI. So with that, I want to turn it over to Yiheng to talk about the next part of the presentation.
All right. Thank you. So since Molly mainly focused on the vehicle systems, I will switch the gear a little bit. Next, like 20-25 minutes, I will talk about the cybersecurity issues from the transportation infrastructure perspective. So we all know that the connected and automated transportation system enables a lot of new opportunities for the infrastructure operations as well. Here I give a few examples like how to leverage the cooperative perception to improve the vulnerable road user safety, right? And also how to utilize the new sensors like the connected vehicle trajectories or the perception sensor data to optimize traffic signals to improve mobility, or can also leverage the infrastructure side information like SPAT and the map, like what Paul just presented, right? So the Tosco project, how to utilize this information to do eco-driving and speed advisory to save fuels and to reduce emissions. So, however, these new technologies also brings new vulnerabilities to the transportation infrastructure as well. So this figure kind of shows the cyber risks from the infrastructure's perspective, because now we're installing, perception sensors, right, and also add V2X communication systems, and also there's also edge computing platforms at the infrastructure. So actually, some of the attack models that can be applied on the vehicle side can also be applied to the infrastructure side. And I listed a few literatures that talking about how to attack sensors, how to attack V2X communication systems as well. However, there are also similarities and differences. If I just take what Molly's example about that LiDAR spoofing attack, right? If we install LiDAR sensors at the infrastructure to detect the traffic, essentially the same attack model can be applied to the infrastructure side, where we can also spoof or generate some fake laser to shoot the infrastructure LiDAR as well. However, the impact of the attack may be very different. We all know that the impact is a combination of the likelihood and the risk. The risk can be very much different. So we all know the risk is a combination of the likelihood and impact, right? So from the likelihood point of view, such attack that implementing to the vehicle is actually more difficult because the vehicle is in a constantly moving state. However, this same attack, if we target on the infrastructure LiDAR, it would be much easier because the infrastructure LiDAR is always in the fixed location, right? From the impact point of view, if we create a fake object or a fake vehicle on the road, that may cause a sudden brake of the vehicle that may lead to a rear-end crash, or at least the driver or the passengers will feel very uncomfortable. However, from the infrastructure side, also depends on the different applications, right? If we are thinking about the traffic signal control, previously I have 30 vehicles approaching the intersection, now I have 31. That might not be a big deal, right? And the resultant traffic signal plan may not even change. So my point here is that even similar attack models can be shared between the vehicle system and the infrastructure system, but the risks and the impact should be analyzed case by case. Okay. So next, I will use the traffic signal control system, which is one of the most important infrastructural operations as an example to illustrate some of our works related to both attack and the defense. So I tried to categorize the traffic signal control system by with two dimensions. One dimension is the data collection method, and the other one is the control model. Okay, so the first combination is our traditional implementation, right? The traffic data is collected from the loop detectors, and then we apply some role-based controller, like actuated traffic signal controller. We just use gap out or max out to time the signals, right? And the vulnerability is actually, because the model is really simple, it's just the role-based, does not have a lot of vulnerabilities, but the data may have. So if the data is compromised, then we may have problems. Then the next combination is people started to investigate this from 10, 15 years ago. A lot of work has been done by Dr. Liu's group. For example, we utilize connected vehicle trajectories, right, as the data input. And then the controller is actually a model-based controller. Usually we have some sort of optimization model behind the scene and try to optimize the traffic signals based on some objective functions like minimizing the delay or maximizing the throughput and so on. So in this case, actually, besides the data, we can also compromise the connect vehicle trajectory data to damage the system, but the model itself may also have the optimization model, or the traffic state estimation model may also have the vulnerabilities. Okay. And then this is very recent years, right? People started to look at how to utilize perception sensors to collect the traffic data, creating, for example, a cooperative perception environment. How to utilize this data to do the traffic signal control. And then also more and more people are interested in applying the machine learning algorithms into as the control algorithm. So we're looking at a transition from a model-based approach to a learning-based approach, right? And in this case, then besides model and the data, because now we have perception sensors, the sensors can also be vulnerable. So we can see that with more and more components added to the system and the system becomes more and more complex, there are also more and more vulnerabilities in the system. Okay, so let's take a look at them one by one. So the first combination is loop detectors and role-based controller. Actually, for this combination, this is widely deployed in the US. About half of the intersections are like actuated traffic signals, right? Actually, for this case, there was a real-world hacking example. A couple of years ago, there was an Argentina security expert hacked into New York City's traffic signal control system with this wireless device. So basically, when the loop detector collects the data, instead of connecting a wire to the signal cabinet, they use some like Bluetooth or some wireless technology to transmit the data back to the traffic signal control system. So that's the vulnerability this expert is leveraging, so that he can manipulate the input to the traffic signal control system, right? So, and then to influence the traffic signal timing. And we kind of replicated this attack model. Of course, we cannot do it in the real world. So we basically conducted a simulation study that the attack model is the same. We spoof the wireless detected data, and the strategy is basically to add or subtract the number of vehicles on the selected loop detectors, because this is how the actuated controller work. So this slide shows a general result, and the left figure shows without attack. This is a normal operation. This is a time-space diagram, and you can see the shockwave and how the queue is propagating at the intersection. On the right-hand side, this is under attack, and you can see that how fast the queue start to propagating and what the actual delay. Actually, the actual delay is more than 500% for the single intersection. Then we further extended this into a network level, and this is actually the Plymouth Road from Barton to Green intersection, just north of the University of Michigan campus. So we only attack actually one location, right? This westbound through movement, and we just try to manipulate the detected data on this movement, and you can see this cascading effect. The delay is propagating through the network, right? Even some side street is also impacted, right? And in this case, we are able to increase the delay more than 300% at the network level. Okay. So the next example is the CAV-based, connect vehicle trajectory-based traffic signal controller. In this case, although we still manipulate the data, but actually the vulnerabilities lies in the model part, because usually for the current connectivity situation, we're actually looking at a partially observable environment, right? Because the penetration rate of the CAVs are not 100%. So there is a kind of a pre-step before you need to do signal control, is we call traffic state estimation. Basically, the purpose is to estimate the full traffic condition based on those partial observed information. So there's some vulnerabilities in this step that if we can create some certain extreme traffic feature and input to the traffic state estimation model, and that can kind of amplify the error in the traffic state estimation model and then create a very bad traffic signal timing plan. Okay, so this is kind of the attack idea. So our attack model or threat model is we assume that some of the vehicle owners can be malicious, so that the vehicle, the vehicle information in terms of the basic safety message can be compromised, like containing wrong vehicle speed and location information in the BSM. And this compromised BSM is kind of mixed with the benign BSMs, right? And all of these messages are sent to the roadside unit and then input to the traffic signal controller to make a control decision. Okay, and the attack strategy is because this is we want to falsify the BSMs, right? And so essentially we want to generate falsified vehicle trajectories to launch the attack. So the generation process is formulated as an optimization problem. I don't want to bother you with the math, but the idea is that we want to generate as realistic trajectory as possible while achieving the attack goal. Okay, so attack goal means that we want this trajectory to achieve some trigger some extreme traffic features. So basically, if you look at the formulation, including the objective function and some of the constraints, we try to mimic the car following behavior. We try to keep safe distance to other vehicles. We want to follow the vehicle dynamics and consistency check and so on. Basically, we want one, to make the trajectory as realistic as possible, and second, to make the attack as sincere as possible. Right, so we don't want this is kind of the attacker goal, and so one of the constraints here is to achieve the attack goal, basically to create this traffic condition, and this is kind of one generated for falsified trajectory. It looks pretty normal, right? Until at the end it started to slow down. This behavior is to try to trigger this attack. Okay, so let me see whether my video works. So this is also a simulation study that we did. Actually, this is Huron Parkway and Plymouth intersection. Okay, look. Which one is click on? Oh, no, it does not work again. Okay. Anyway, so so basically we want to show in this video. Actually, that's fine. The screenshot is actually very good. I mean, we want just to show the difference without attack and with attack, right? So the left is without attack. Basically the traffic signal controllers leverage this conduct vehicle information and do the optimization. The intersection looks pretty good. And on the right-hand side, if we just mix one falsified vehicle trajectory, then this is the damage. This is the congestion after 20 minutes simulation. You can see the queue, especially for the left turn vehicles, right? The left turn lanes are already being spilled over, so that it even influence the through movement vehicles. Okay, so right. So then finally, the third combination, this is our very recent work. So when we involve the machine learning algorithms into the framework, then we know Molly also just introduced that the machine learning algorithms have vulnerabilities, right? In this case, because technically the traffic signal control is a sequential decision-making process. So usually we model this as a reinforcement learning problem, or in this case, a deep reinforcement learning problem, right? So when we involve the deep neural networks, there are also vulnerabilities there. So in this setting, we're looking at a specific type of attack called the Jacobian-based saliency map attack, JSM attack. This saliency map was originally proposed for the image processing, for the image classification purposes, but we try to also utilize by analyzing the saliency map to find the vulnerabilities of the deep neural networks. So the key idea is the saliency map can tell us that which features have more influence on the decision. So then based on this analysis, we can manipulate certain features to generate the desired action that we want. In this case, the the features are the traffic states, and the desired actions are the traffic signal faces that the attacker wants. Okay, so so here is some results. Sorry, I just because of the time limit, I just skip some of the methodology, but just to directly show you the result. And so you can see also it is very effective, right? So the blue line shows this normal operation on the different CAV penetration rates, and the orange and the green curves shows the result under attack. We can also, increase the delay for about more than 200%. It's very, very effective. Okay, so from here, so we can see that no matter how the system is, what is the control model or what is the data input, we can always find vulnerabilities, right? Actually, it is very difficult to design a system that is free of any errors, free of any vulnerabilities. So then the next question naturally would be how to detect the attacks and defense system, right? And also, unlike Julie and Molly, who are computer scientists and electric engineers, so we are traffic engineers. So we try to tackle this problem from the traffic engineering perspective, right? So because this is the CAT system is a kind of multi-layered system from the software, hardware level, software level, communication up to the application level, which is the traffic applications, right? So we try to utilize the traffic domain knowledge to do the defense. Okay, and also we always want to have a pessimistic view when we design the defense system. We want to put more layers of protection, so that now the attacker not only needs to be a computer scientist, but he also needs to be expert in traffic engineering in order to penetrate the system. Okay, so because we are kind of located at the last layer of the system, so we consider ourselves as the goalkeeper in the soccer game. So the main idea or the main direction of the defense is the anomaly detection, or sometimes we call this misbehavior detection, because after analyzing the attacks or the attack trajectories, we find that in order for the attack to be succeed, the attack vehicles always appear some abnormal driving behaviors. Okay, so like in this case I showed before, the vehicle started to slow down at the end to achieve the attack goal, but its leading vehicle is still far away. So this is actually a abnormal driving behavior. Normal drivers wouldn't do this, right? And the video actually a little bit, maybe a little bit too small, shows another vehicle behavior under this GPS spoofing attack. This is more like a lateral abnormal driving behavior. The vehicle will, there's a red vehicle here. Actually, this vehicle when it's under attack, it fluctuates within the lane and finally deviate from the lane to the outside of the road. Okay, so this is more like the lateral abnormal driving behavior, right? So our kind of solution direction would be how to identify those abnormal vehicle trajectories using the traffic domain knowledge, for example, the traffic flow models. Okay. So the first work we have done is that this work is actually inspired by the word embedding model from the natural language processing community, because we find out that the trajectories actually has a lot of similarities with the sentences. So trajectories consist of trajectory points, and each sentence consists of words, right? And it's not a random combination of words. Each sentence have a meaning. Each trajectory trace also has a meaning, representing a certain driving behavior. Could be car following, could be lane changing, could be startup, could be slow down, could approaching or departure, and so on and so on. Right, so we try to consider the trajectories as sentences and apply the natural language processing model to represent the trajectories. So what we did is, given a trajectory, right? First, what we do is encoding because we want to encode it to the sentences, right? So we select the features from the trajectory traces, and in this case, for each trajectory point, we have 3 features. So each trajectory point can be encoded into a 3-letter word, and then we combine the trajectory points together. For a whole trajectory, we have a sentence like ZBI, YBI, something. It's not a human readable sentence, but it actually represents some driving behavior. Okay, so then the next step is we train a neural network to get the vector representation of each trajectory point. And then after we getting the vector representation of each trajectory point, then we can utilize the vector and comparing the vectors from different trajectories and calculate the vector distance. And we use the vector distance as like a similarity or dissimilarity matrix for comparison. So finally, we do a clustering, meaning that the similar trajectories, or the trajectories have similar driving behaviors. They have smaller distances, right? And the trajectories have different behaviors, like an abnormal trajectory. It will have a large distances with the normal trajectories. Okay, so here are some results. We tested this on different attack models, right? You can see they have different abnormal driving behaviors, and after the clustering, we can always differentiate what are the normal trajectories and what are abnormal trajectories. And we do another case that if the attacker does not have a specific attack goal, he only wants to generate a very realistic vehicle trajectory, then our model also cannot identify them. But those normal trajectory, even they are fake, they may not have big impact to the traffic system. Okay. So the limitation of the previous work was that we only consider the longitudinal driving behaviors or the longitudinal anomaly. But you know that we all know the driving, right? We have both longitudinal and the lateral behaviors. So in this work, with last year's work, we tried to combine the longitudinal and lateral behaviors together. So the idea is that we try first we try to train an agent, use imitation learning to train the agent to learn what is the normal driving behavior. Okay, what is the normal driving behavior? And then we also train a classifier to differentiate what is normal and what is abnormal. And then in the execution stage, when we want to do the detection, given a start of the trajectory, we first use the learned agent to predict what should be normal, because that agent already knows what is normal. And then we compare the predicted normal trajectory with the observed trajectory. And then it's similar. If the two trajectories are similar, then we consider this is a normal trajectory. When the predicted trajectory and the observed trajectory have large deviation, then it is a abnormal vehicle trajectory. Okay, and so we tested this on this data spoofing attack. As I mentioned, this is the same attack model when this red vehicle is under attack. Right, in the first stage, actually, this vehicle deviate from within the lane. The deviation is small. At the second stage, actually, the vehicle, you can see, started to deviate from the lane to the other lane or to the side of the road. So we can see that during the first stage, it's not very dangerous, right? Because although it's fluctuating, but it's within the lane. But however, in the second stage, it is very dangerous. So our goal is try to detect this anomaly before the second stage. Okay, before the vehicle deviating from the lane. So actually, the algorithm shows very good performance. And actually, in every test case we conducted, the algorithm can always detect the anomaly, abnormal driving behavior within the first stage of the attack. And if we compare this mean time to attack success, it's about 16 seconds, which leaves enough time for the vehicle to react. For example, ask the driver to take over, or revocate this security certificate and so on. Okay. I think that's all I have, and then Julie will summarize this work and talk about some our future visions. Oh, sorry, I think I did something.
Okay. So
You want this?
that's all. Okay, so from what Molly and Yiheng had talked about, right? So you understand securing the next generation connected automated transportation system is really a complex, challenging task, right? So there's many type tasks available, possible, and especially with the AI that can help us make system more intelligent, but on the other hand, also introduce a lot of kind of new attack, right? So how do we actually really effectively cope with the complexity dynamics of the such a system to actually secure harden, right? So it's almost like hopeless. So, so in particular, also the communication infrastructure itself, technology has also evolved, right? So from DSRC wave to cellular V2X, and people looking at 5G or NR, V2X, etc. Right? And how we actually also enable many, many different new applications, right? So we had the secure harden. So from the morning in the panel, you know that if you don't design a system, people are going to trust it's not going to work, right? So many of the systems we talk about are going to be in the cloud, right? So the question, how do we actually secure the system? As Yiheng mentioned, I'm actually a computer scientist, and also in particular, my expertise in networking communications, so I like to think architecturally. So again, so if you look at some of the system people talk about, so Yiheng don't take it the wrong way. So I criticize the transportation engineer, or Henry for that matter, right? So oftentimes if you look at some of the system, people are looking at cooperative cruise control system, then say, hey, how we can use V2X, or you design intelligent traffic control, looking at how we're going to use V2X. So the problem with such a system, what I see from the networking architecture point of view is the stovepipe kind of design. So everyone designs this separately. So what's the problem with this case? Right, so you end up coming with ad hoc security mechanism for each individual system. You try to design your own security mechanism, right? So the problem also when you design system, there's no code reuse, end up adding a lot more complexity because more kind of bloated software system, you're going to adding more kind of possible vulnerability, right? So also make it much harder to leverage new capability. Again, for example, think about we have 5G, 4G already existing, and if you want design system to leverage new communication capability, you end up having to changing individual system also, right? So the idea is how do we actually secure such a system? So the bold vision idea is that we want to introduce a next CCAT operating system, right? So such a system would provide standardized APIs, right? So this API could include both separate, in particular with a unified integrated communication layer that provide, for example, a source-bound APIs, right? So this is communicate using different type of communication technology. You also have so-called a northbound API providing information to the CCAT cooperative intelligent transportation system applications. So each of these applications doesn't have to worry about individual communication, which V2X technology should I use, or should I use in 5G, etc. Right? So the advantage of this also going to enable, make it easier to actually incorporate a new type of communication modality. For example, satellite communication, right? So you can use Starlinks, for example, by adding Starlink dishes in the both infrastructure or in the cars themselves. You want to be able to take advantage. And the idea is that then you can foster new type of cooperative intelligent transportation system. So with such a CAT OS, from the security point of view, now we can actually provide key security primitives, right? So now we can actually secure some of the communication interfaces, etc. Instead of individuals, application had to worry about how to secure themselves, right? So we can provide some primitive, but also have enhanced security service with additional kind of security service that can fit into this CCAT applications. Right. So just some example of key security primitive, right? So one would be the device authentication. For example, you can rely on the USDOT's, the security credential management system, right? But on top of that, for example, we can also incorporate, for example, 4G, 5G cellular network with the SIM card. You can actually authenticate those systems. Right? Other would be secure location service, right? So you can mention about you can do GPS spoofing. So if you purely just rely on vehicle GNS system, you may be able to actually spoof some of the GPS. But on the other hand, we can also add in additional kind of information sources to help the vehicle to actually secure its location and getting kind of localization information, not just rely on your own information. Right? Others, with such a CCAT system, we can do monitoring and telemetry to provide information to the vehicle themselves. For example, the number of vehicle traffic flow. Right? So someone can't just figure a new vehicle because there's certain continuity. Right? Other thing would be verification, attestations. Right? So for example, does a vehicle with a particular pseudo ID actually exist? Right? So we have observation. We can actually see whether test such a vehicle actually exists. Test not only just at a device level, but also at a message level. You say this message is actually secure. So in terms of, for example, some additional enhanced security services, right? So we can provide dynamic 3D map for situation awareness, right? So some of the attack defense mechanism I could touch on can actually provide additional information, right? So it can not only just provide device authentication, but also verify the data and content verification, right? So a lot of the attacks you heard earlier rely on the ability to falsify data, inject some false data, right? So if you have such a CCAT OS system, we can actually verify those data, verify the content of the data, right? And do multimodal kind of misbehavior detection, right? So anomaly detection, we rely on both to protect individual vehicle or transportation systems, right? So with such a system, we can actually help detect anomaly and actually identify misbehavior detection. Right? So that's basically the vision we're actually interested in looking at. Right? With such a system, you can also kind of building new business models to proper, for example, OEM to actually adding its own vehicle security services to secure their own vehicles, or you have mobile operators that actually interested in adding V2X security. Road operator can actually run in security services, and also government, for example, can having cybersecurity transportation defense center. Right? So this is potentially important for attack against terrorist organization, nation state. Right? So you want to be able to do that. So that's basically what we're interested in looking at. And a few slides just kind of give you some cartoonish to show why, for example, if you try to just secure V2V by itself, it's hard, right? So this is the problem in the networking system we have looking at. If you try to just secure a purely peer-to-peer system, actually very hard to do, right? So for example, we know that the USDOT has this security credential management system that can help identify kind of essentially authenticate the devices, right? So that's actually provide some basic trust, at least to say, hey, this vehicle has a trusted onboard unit or roadside unit by itself are not sufficient, right? So for example, if your car is suddenly braking in the V2V message, you say, hey, I'm braking, right? But that car is not authenticated. Should I ignore the message or not, right? Or you may have a vehicle say, hey, I'm traveling at a very fast speed, but actually travels much slower. It's coming from an onboard unit that is trusted. Should I just trust that message, right? So that's not sufficient, right? So with this CAT OS system, we can potentially use information we have observed in the past, recent past, right? So we can say, hey, this is, even though this car's sending braking is not authenticated, but we actually seen this car before. We know that it's not misbehaving, so we may want to take that message and take some action, right? Or you may have a vehicle that is authenticated, but on the other hand, we actually detect this vehicle has misbehaving, right? So we can actually report that to the system, so we can detect misbehaving system, right? So this is basically try to illustrate why I think this such an operating system would be useful and help us building a kind of unified way to building future cooperative intelligent transportation system service, right? So I'm gonna just, I want to make sure we have time for questions. I can quickly just flush through, so how do we actually design a system? Right now it's just a vision idea, right? So again, how do we design a system? This is where we can leverage a lot of principles, design principle, and also practice we have been building in the past 20 to 30 years, right? So some of the design principle, in particular network design principle, we want to design such a system that can be zero trust, right? So we're gonna be able to authenticate the devices, right? Not only devices, but also user data, etc., software. But also, more important, we also want to have in this trust but verify type of principle, right? So just because devices authenticated doesn't mean the message we're gonna trust, or the device is not authenticated doesn't mean the message should be ignored, right? So we want to have a way to verify those things. Other principles like isolation, for example, we want to isolate trusted component from untrusted component, and also the messages, etc. Right? So to prevent insecurity or vulnerability spread from one system to another, we want to be able to continue monitoring, testing, auditing, see what's really going on, and also importantly, also provide user data privacy protection, right? So other part, we want the system to be software-defined programmable, because the environment changes, things are gonna change, right? So we want to program the system. It's policy-driven, gonna depend on different type of environment, right? So urban, busy kind of intersection might be very different from the rural, etc. So again, I'm gonna just quickly list through some of the design principles, right? Separation concerns, modular design, and loosely coupled, right? So the idea is that we want to design such a system that can be future-proof, because you deploy the system for the infrastructure, they're gonna last 10 years, 20 years. Right? So you want to be able to accommodate such a system. Other things we'll talk about, and in order to secure the hardened system, we want to explore diversity, different type of sensor, different type of data, different type of algorithm, software, etc. Right? And most importantly, such a system had to be do no harm, right? So in the sense that if the system failed or such a system not available, we shouldn't compromise the security or the safety of the system, right? The vehicle is still going to have autonomy to make decisions, right? So we are not dictating the behavior of the system, right? So lastly, the most importantly, the system had to design safety first, right? So that's the most important part. We should prioritize the safety over, for example, traffic efficiency, etc. Right? So, and it has to be human-centered, right? So again, human had to trust, right? So the human, both from the kind of road operator point of view, vehicle, OEM, etc., but also from the user point of view, right? So if I get into a car, should I trust this particular car, etc.? So we want to have allowed to design the system, allow human on the loop, right? So take a intervention when needed, right? So for example, we have certain misbehaving cars or certain things we maybe actually need to getting the cop involved to stop that car, right? So those are kind of general system. We need to mitigate the risk of AI by combining human and machine intelligence, right? So that's the kind of basic principle. So I want to stop here so give enough kind of time for questions, right? So we have kind of essentially give you an overview of what the potential new type of physical cyber threat, and give you a lot of examples, and in the end, we provide you kind of vision that we want the community to work together to building what I call the next CCAT OS systems, so that we can secure the whole system. So anyway, so thank you very much, and this is our contact information, and we really welcome questions and comments and feedbacks, right? So want you guys want to stand up here, so.
Does anyone in the room have questions? Okay, hold on 1 second. Let me give you a mic.
Any questions?
No, go ahead. Well, thank you so much for a wonderful presentation. So it's a lot of information to digest. So my question is for Marley. Am I pronouncing it correctly? Okay, so forgive my ignorance. One of the challenges for me to understand how this is relevant in some sense is, so I think I have two questions. One is, in order to do any of those attacks, did you assume that you have the knowledge of what is the perception system on those vehicles, or did you have access to that perception system?
Yeah, that's a good question. I think in some cases we assume it's a black box attack, so we don't know the underlying machine learning model. But in some cases we have a white box attack where we have a detailed knowledge of the machine learning model. So there are some, obviously black box attacks are more difficult to carry out. So there are, depending on which one it is, there are some differences. Yeah, so, and also we assume the attacks could be against, so it could be adaptive attack, meaning that attacker could be smart enough to know that this defense could happen, it will adapt its behavior. So there are different threat models in place. Yeah, in general, I think the assumption, but I think it's also the general principle of security by obscurity is not a good assumption, right? You shouldn't assume your models are not known and therefore it's secure, right? It's always good to assume, people could get access to your model.
Right.
Yeah?
So my question is essentially, what is the value of going through all these processes to attack a single vehicle? What do you get out of it? So I understand, like, if if someone wants to assassinate someone, that might make sense.
Yeah.
But if you go through all these processes to just stay on the side of the road and attack a car,
you mean the attacker incentive, right?
Right. So what are you trying to prevent? What are the possible cases that you're trying to make sure that doesn't happen?
Yeah, I think that's a good question, because usually attackers, you have some economic incentives, or maybe it's nation state attacker, then they are targeting specific victims, right? But in general, in this case, we do not have a careful study of the attackers' kind of incentives. So we just assume that they're trying to understand from the very beginning whether such attacks are feasible, then how expensive it is to carry out these attacks. But in all our study, it's not very economically very high cost to carry out these attacks, meaning that these kind of off-the-shelf kind of LiDAR sensing, we build our own LiDAR spoofer, for example, right? Whether attackers are motivated to do these attacks, maybe they want to cause traffic disruption, right? There could be some, malicious entity, a nation-state hackers, right? So, it's arguable whether these attacks will happen in practice, but at the same time, we do need to make sure the systems are safe enough if these attacks are likely, because they are feasible. It's not that impractical. Does that answer your question? Yeah.
So, I mean, basically, we want to understand the feasibility of attack and also mode of attack, right? So, for example, a lot of the attack rely on some kind of data falsification, et cetera, right? So that's help us to understand if we want to design a mechanism, where should we protect? Right?
Yeah. So if it seems to me that for someone to actually be able to conduct a spoofing attack on a moving vehicle, they would have to go through a lot of trouble to do that. They would have to synchronize their own speed with the vehicle, have their vehicle equipped, and then they're only targeting a single vehicle in that process. It seems to me.
I think there is to that comment. I think to Yiheng's presentation, right? There is this also the infrastructure LiDAR sensor.
Exactly. I was going to say that's a much more viable.
Sure.
Case.
That's a fair point, but you could imagine maybe just at a busy intersection, right? Attacker could set something up just to because it has a lot of potential victims, right? So I agree, it's not always clear where the motivation comes from.
I worry about the infrastructure, because I think we are now talking much more about installing roadside units and providing the sort of information that AVs and ADAS systems can utilize. And I think we are also creating an opportunity for bad actors to come in and impact these units. And I think that's a big problem. I'm going to ask a quick question from Dr. Feng, and that's on your anomalous trajectory detection. Every traffic situation creates its own sort of setting where a normal driving for that traffic situation in that instant or over a relatively short temporal horizon is going to be different from normal driving over another time window, maybe several hundred feet away, several seconds away. So then this idea of defining uniquely what's normal driving from abnormal may become sort of problematic, wouldn't it?
So that's why we want to incorporate some like physical laws, like the traffic flow models, to make this detection model more generic, right? We don't want to kind of case by case and analyze, like you said, for different time windows, for different locations, for different traffic conditions. They may all be different, but actually the traffic laws are universal. When you have a very congested congestion, you may have a shorter headway with lower speed. So when you capture the relationship between your own vehicle and your surrounding traffic, then this kind of detection can be applied to different situations.
Any other questions?
Thank you for the presentation. I learned a lot, I feel. So I just want to follow up on that. So your detection is based on detecting abnormal behaviors. What if you have a genuine incident, accident, right? How do you deal with that? Would you rely on actual perception to detect that? Or if it's in software, if some vehicle actually stored, right? Would you say this is abnormal, so ignore it?
So that's a good question. But so one thing is that this is still some abnormal kind of driving behavior. Then we need to dig further whether this is caused by an accident or some mechanical failure, or this is caused by cyber attack. But from the traffic management point of view, we still want to remove that vehicle information, right? Because this is still this is not the accurate information we want to capture. But I do agree with you, we need a deeper, investigation. What is the cause of the anomaly? Yeah.
Oh, yeah. Could the attack come on foot, like with a cell phone sitting at the intersection, not looking fairly normal?
Actually, the video does not really work. Our attack model actually in the connected vehicle trajectory attack is assuming that the attacker sitting at a gas station nearby, because in the current V2X communication system, everything is in broadcast mode. So everyone can hear everyone's message, including the attacker. The attacker can also hear the benign messages, the traffic signal timing, the map, everything, so that he does not need to be on the road to perform the attack. So it also makes it more sincere.
Last call for questions.
Yeah. So wonderful presentation. You guys are doing some really cool stuff here. So I have a question from the vehicle system portion of the presentation. So when you were discussing about the adversarial attacks, and you were talking about the temporal order of events, right? So from attacker's perspective, how does the attacker ensures that there's no anomaly when he's trying to inject some kind of adversarial attack in the temporal order of the events?
Can you just want to clarify what you mean by anomaly?
I guess it was slide 123, I think.
Okay, we can go to that slide.
123. Yeah, let me see.
123. Maybe 123. This one? Oh,
I think I need to.
Yeah.
Okay.
Exactly.
Okay.
Okay.
Yeah.
So what I'm trying to understand is whenever the attacker is trying to inject some kind of malicious data in the sensor feed, right?
Yeah.
There is definitely going to be some kind of anomaly in the order of events. And that could be detected, right? So how would an attacker ensure that there's no glitch or no sudden kind of anomaly?
Oh, I see. You mean because it's multiple frames that it appears to be some
Like there-
lack of continuity.
Yeah, because the frames are following some kind of temporal characteristics, right?
Right.
And if the attacker is injecting some malicious data, right? So there's definitely gonna be some kind of an obvious.
Yeah, I think it's a
frame
good
with-
question. So it's basically, I think the vehicle system is very it looks at each frame and makes potential decisions based on each frame, right? So you're saying maybe the attack only happens in a single frame. It's very discontinuous from the
Yeah.
previous frame.
Mhm.
Yeah, that's a good point. But at the same time, the system should be conservative enough to be able to respond quickly, right? So there is a tension between, not very reacting to discontinuous events, but at the same time you want to be conservative and safe. So I think in general, attacker could be smart enough to inject something for several frames, so that way it's appears to be more normal, right? But at the same time, I think we have demonstrated that actual Apollo Baidu's perception data processing pipeline software is susceptible to the attack we artificially created.
Okay.
So it shows that the version we have is open source, so it may not be as robust. So I think it is possible, it's a fair point. There could be some built-in anomaly detection system algorithm into the data processing pipeline to detect these deviations.
Yeah.
But I think you also have to be careful, right? Because there is essentially a tension between being more conservative versus able to detect these truly unusual behavior. Because you can have some pedestrian often crossing. Does that mean it's anomalous, or this is actual real pedestrian, right? Because things happen very quickly in the actual live traffic scenario.
Yeah, it's
Yeah.
always a challenge to distinguish between like a faulty situation and a
Yeah.
intentional kind of attack, right? So
Yeah, exactly. Yeah, that's a very good point.
Yeah. All right. Thank you. Thank you for the answer.
Thanks for the question.
I think we have time for one more if somebody wants to ask one. Okay. All right. Well, thank you, professors, for your time.
Thank you.